Let us perform another experiment, which is a little different from the ones before. First, we use a 90-degree pulse. The longitudinal magnetization is tilted. We get a transversal magnetization. What happens after this pulse when we wait a short time? After the pulse is switched off, longitudinal magnetization starts to reappear. The transversal magnetization, however, starts to disappear. Why does the transversal magnetization disappear? It is because the protons lose phase coherence, as we learned earlier. The loss of phase coherence results in decreasing transversal magnetization and thus loss of signal. Now we will do something new. After a certain time, which we call Te divided by 2, that is half of Te, for reasons you'll understand in a few minutes, we'll send in a 180-degree pulse. You can activate the pulse by clicking on it. Then watch what happens. What happened? Let us rewind and watch the scene again in super slow motion. This is the situation when the protons are in phase right after the 90-degree pulse. Shortly afterwards, they start to lose phase coherence. Then we sent in the new 180-degree pulse. The 180-degree pulse acts like a rubber wall. It makes the protons turn around so that they precess in exactly the opposite direction, which is clockwise. The result is that the fast precessing protons are now behind the slower ones. If we wait another time, half of Te, the faster ones will have caught up with the slower ones. At this point in time, the protons are nearly in phase again, which results in a stronger transversal magnetization and thus in a stronger signal again. A little later, however, the faster precessing protons will be ahead again, with the signal decreasing again. To illustrate this, think about the race between the tortoise and the hare, starting at the same line. After a certain time, half of Te, the hare is ahead of the tortoise. When you make the competitors run in the opposite direction, for the same length of time,
run back!
They'll both be back at the starting line at exactly the same time, assuming that they run at constant speed. In our experiment, the 180-degree pulse acts like a wall from which the protons bounce back, like a mountain reflecting sound waves as echoes. This is why the resulting strong signal is also called an echo or spin echo. After we have our signal, our spin echo, the protons lose phase coherence again, the faster ones getting ahead as we have seen. We can naturally perform the experiment again with another 180-degree pulse, and another, and another. If we now plot time versus signal intensity, we get a curve like this one. A curve connecting the spin echo intensities is the T2 curve. From this curve we can see that the spin echo, the resulting signal, decreases with time. Responsible for this is the fact that our 180-degree pulse only neutralizes effects that influence the protons in a constant manner, and these are the constant inhomogeneities of the external magnetic field. Inconstant inhomogeneities from local magnetic fields inside of the tissue cannot be evened out, as they may influence some protons before the 180-degree pulse differently than after the 180-degree pulse. So, some of the protons may still be behind, or in front of the majority of the protons that'll reach the starting line at the same time. So from echo to echo, the intensity of the signal goes down due to so-called T2 effects. Maybe we should illustrate this by an example. Imagine two buses full of people, for example after a soccer or football game. They're standing at a starting line. With two microphones, you record the signal, for example, the singing from the crowd that is coming from each bus. The buses leave in the same direction. Listening to the singing of the crowds, in other words, recording the signal, you may recognize that one signal disappears faster than the other. This can have two different causes. The difference in signal intensities, the difference in singing, may be due to differences in inherent properties of the two groups, internal inhomogeneities. Maybe in one bus there are only the party animals, who did not become tired as fast as the people in the other crowd. Or maybe one bus is driving faster than the other. Loss of signal would thus be due to external influences, the external magnetic field inhomogeneities. To figure out what the actual reason is for the signal disappearing, you can make the buses turn around after a certain time half of TE, and have them drive back with the same speed also for the time half of TE. After 2 times half of TE, equaling TE, the buses will be back at the starting line. The signal intensity that you record with your microphone then depends only on inherent properties, in other words, how tired the crowds have become. Let us have a look at our curve when we plotted time versus signal intensity, sending in several 180-degree pulses. If you do not use a 180-degree pulse to neutralize constant external inhomogeneities, the protons will experience larger differences in magnetic field strength when the RF pulse is switched off. Due to this, they will be out of phase faster. The transversal relaxation time will be shorter. A curve describing the signal intensity in that case is the T2 star curve. The star distinguishes this shorter transversal relaxation time from the T2 after the 180-degree pulse, which we've already talked about. The corresponding effects are named T2 star effects. These T2 star effects are important with the so-called fast imaging sequences. We will hear about them later. The type of pulse sequence that we used in our experiment is called a spin echo sequence, consisting of a 90-degree pulse and a 180-degree pulse, causing the echo. This pulse sequence is very important in MR imaging, as it is the workhorse among the pulse sequences, which can be used for many things. It is important to realize that with a spin echo sequence, we can not only produce T2, but also T1 and proton density weighted images. We'll get to that a little later. Let us first look at such a T2 weighted sequence.